concave down to concave up. And you probably saw in your class where maybe you're holding your hand, like you're holding your hand down, you're holding your hand up.
So there's concave down, concave up. That only happens once here.
So there, like to me, there's an inflection point. I've got my mouse where there's one. Like I see two inflection points. I see it goes from concave down, then concave up, and then concave down again.
Mm-hmm.
And
okay. All right, concave down to concave up, that's 2. Concave down, concave up, is that 4?
one. So I'm seeing like between the min and the max, or sorry, between the max and the min, there's one in the middle.
Mhm.
And then there's one again between the min and the max, and then another one between the max and the min. So 1, 2, I see 3.
All right, here we go.
So look like the graph of a function which has exactly one critical point and exactly one inflection point. So a critical point is where the horizontal tangent equals 0. So at 4, does it equal 0? I mean, it doesn't actually look like it's at 4, but I guess it's close enough.
Well, there are others.
Okay. So like that, I don't know, the second from the bottom, it for sure has a critical point at 4 because there's a horizontal tangent there. Now at 6, does it change inflection?
It looks like it does.
It does. It sure does.
Inflection points. All right. During a flood, it rose faster and faster and rose more and more slowly until it reached the highest point. That went back down to pre-flood level. The time of highest water level, isn't that a critical point? Or is it an inflection?
Highest water level is a critical point. And we could draw a picture of this. It would actually look very similar to what we saw in the previous problem. Would you like me to draw a picture of what this looks like?
I will look at B first and then you
Okay,
can
you may not. Yeah.
Is the time when the water first began to rise more slowly a critical point or inflection point?
It is an inflection. It's an inflection point because it's changing the rate at which it's changing, which is going to be a new concept for you here. Hopefully that's
clear.
Right. So the way to answer this question here, and I'll probably have to share my screen, is you have to take two derivatives.
Mhm.
Okay, so I'll share my screen, and we'll work through this one together. All right, so you're seeing my screen now. Hopefully you're seeing the workspace. So you got to find f prime of x. So this is why it's so important to be able to take derivatives, because you got to be able to take a derivative without, any thought. And these are all power rule derivatives. So now you take a second derivative, which just means take the derivative of the derivative, 12x squared plus 6x minus 6. And for inflection points, which is what you've got here, you said f double prime of x equal to 0. You set this equal to 0, and you solve for x. And you're going to use all those techniques you learned in all those other math classes you've taken. Here we're gonna factor. We're gonna factor out of 6, 2x squared plus x minus 1, and then we're gonna determine where that occurs. So this is like plus 1 minus 1, and you set each of those equal to 0.
Okay.
So you're gonna set x equals 1/2, x equals minus 1. I think it's said in your problem to put them in like the smallest one first, so that the minus 1 would obviously come before 1/2.
Sounds good to me. Okay, I'll check it. So answer, okay. So in increasing order, do I put -1 for the first one and then
Yes.
1/2 for the second one?
Yes.
Okay. -1, then 1/2. All right. All right. I'll go back to sharing. Here we go.
All right, so this one wants a table of critical and inflection points. All right, so let me grab all of this and then we'll work through it. All right, so I'll share my screen. All right, so I'm switching to the red. So your first derivative is 4x cubed minus 12x squared. And you set that equal to 0. And then from here, you've got to factor out whatever you can. So in this case, you can factor out 4x squared. So you end up getting x minus 3. And you can see that there's a critical point at 0, because that's when 4x squared equals 0, and then one at 3. So the critical points are at 0 and 3. And then looks like it would go NA, NA.
Oh, okay. Why is it put it there 4 times?
So because they probably reuse this answer space for another problem that has it.
Oh, okay.
I mean, you can have like a critical point is wherever the graph, comes down or goes up. I mean, you could have a lot of these on a particular, thing.
All right. So NA. All right. I'm
Okay,
gonna check. So the critical points, like on the side, says local maximum, local minimum, neither maximum nor minimum, or not applicable. Would
Yes.
the third and fourth ones also be NA?
Yeah, they're NA.
Okay.
So to answer the first two, though, you make what I call it's a sign chart, but I just draw a number line, and you put the 2 critical points on your number line.
Yeah.
And then hopefully you saw this in class, because this is somewhat new, is you test a point in each region.
Yeah, that's understandable.
And you
And you
test
want to
like
find it if it's positive or negative to
exactly
determine where you're going.
exactly. Now 4x squared is always positive.
Okay, and
So
that's
so it comes down to the sign of whatever it is in the other regions here. So that's this one is positive. 0 to 0 minus 3 or 1 minus 3 is negative. And then this one is
negative.
is also negative. Okay, and then I've got to give you a little like bit of like, this is important. So if you go from plus to minus, this is a max.
Yeah.
And if you
Isn't
think
that
about
concave down?
no, it could be, but it could also not be. Plus to minus means you're going increasing to decreasing.
Mhm.
Okay, this is all first derivative stuff. Minus to plus is a min. I'll draw
Okay.
that as well. Sorry, that didn't do that. And then the graph here looks like this.
Mhm.
Okay, and then the other possibilities, these are the ones that you got to be looking. That's why you got to test it, because you don't want to just assign these sign. Plus to plus is nothing.
Mhm.
Minus to minus is nothing.
Nothing.
And you will see that. So if we go back to our problem, this 0 is nothing.
Mhm.
So I don't remember what the option there was neither.
Oh.
But at 3, since it goes from minus to plus, it's decreasing to increasing. It's a min. This one is a min.
All right. And then for inflection points, I don't really understand what those are. Like, how do they work?
So we've got the first derivative up here,
Mhm.
and we got to take a second derivative. So I'm sorry, this is kind of all over the place, but I'm going to put the second derivative down here on the right.
Mhm.
So you got to take a derivative of the derivative. So that's 12x squared minus 24x.
Yeah.
Okay. And then you factor out a 12x and you get x minus 2 in here, and you just set those equal to 0. So you set 12x equal to 0, you set x minus 2 equal to 0, and you get the 2 inflection points of 0, x equals 2.
Okay.
So the inflection points, yeah, they just have them here at 0 and 2.
Oh, yeah, they're also applied to the in oh wait. Okay. How did you get 12x squared minus 24 again?
So let's go back to the original thing on the top left here, because that's really what matters here. I'm just gonna rewrite it down here, because in this is like this kind of stuff we're doing the other night, where you just got to get really, really fast and good at it. Let me go see that. So your f of x your f of x is, this is given, x to the fourth minus 4x cubed plus 8. So your f prime of x is the first derivative, 4x cubed minus 12x squared. Is that okay?
Yeah.
And then f double prime of x is just taking the derivative of
Oh,
this, 12x
okay.
squared minus 24x.
Oh, I guess you're supposed to follow it along, I guess.
So um,
They would just factor it out, 12x,
Yeah.
x minus 2. Then you said it
Yep.
equals 0.
yeah, and that's what we did for
Inflection points. That's how it works. It's the second derivative, finding
yes,
the
and
x's.
setting it equal to 0.
Okay.
But in terms of the inflection points, it's supposed to change sign, and we didn't show that in the previous one, but really should have.
All right. I'm gonna share my screen again
Okay.
for the next one. Let me get rid of a couple of these other things that are unnecessary. Get rid of that for now. Here we go.
All right, use, okay, so this is the same type of problem here. So let me grab it and we'll work through it together.
So first you just find the first derivative.
Yep.
That'd be like 5x to the fourth minus 80x cubed. And yeah.
Yep. And you factor out a GCF, which is 5x cubed. So you get x minus 16. And you set both of these equal to 0. So you set 5x cubed equal to 0 and x minus 16 equal to 0. So on the left, it's x equals 0. On the right, it's x equals 16.
Okay, so those are the
Okay.
critical points, and then we find the second derivative, right? And then we set it equal to 0.
But I think it wants to know whether they're mins or maxes.
Oh yeah, forgot about that.
So you gotta test points, in each region. And you're testing them back in the derivative. Okay. And you do not test the critical points. You already know they're 0. So you want to choose values that and are easy to calculate, but you actually only care about the sign. So like you don't, you're just looking for, well, is it positive or is it negative? So this time when I put 17 back in here in this factored form, you generally want to use the factored form.
That's going to be positive no matter what.
No. Cubes could be negative, right?
Oh, wait. Oh, never mind.
So that's why we got to test them both this time. But this one on the right is positive. 17 cubed is positive. So it's a positive times a positive makes it a positive. 1 cubed is positive. 1 minus 16 is negative. Positive.
Negative.
Okay. -1, you get a negative here. Okay. And then this was also negative. So you have a negative times negative makes a positive. So when you go from positive increasing, negative decreasing, that's a max. Here at 16, you go from decreasing to increasing, that's a
minimum.
min.
All right. And now we find the inflection point.
All right. So to find the inflection point, you need the second derivative, and you do not use the factored form. You want to go back to this line right here, and that's the one you want to use.
Yeah.
Okay. So it's 20x cubed minus 240x squared.
And GCF that.
Yes. So you get 20x squared goes into both, x minus 12. So you set them each equal to 0. So you get 20x squared equals 0.
So it should be 12.
Yes.
All right.
And x equals 0. Okay. And then to do it right, you're really supposed to do the same thing you did for the first derivative, which is you're supposed to make a chart here. They sometimes make tables in the classroom. I don't really remember, but I think the number line's better. Okay, and you go back to the factored form again. So notice these are like potentially substantially longer. X squared is always positive, so it's just based on the sign inside here. So this one is plus, this one is minus, and this one is minus. So this right here is the only inflection point because it's the only one where it changes sign. Minus to minus is not a change of inflection. Plus to plus is not a change of inflection.
All right. Sounds good to me. All right, I'll share my screen for the next one. Here we go. I keep forgetting, like, okay, so inflection points are where it goes from a concave down to concave up, basically.
That's true, but this is not the graph of the original function. It's the graph of the derivative,
Oh,
the second derivative. So because it's the graph of the second derivative, an inflection point occurs where it crosses the axis.
mhm.
So at -2 and 1, those are the only inflection points, which
How come 0 isn't a part of that? Why is it just kind of there?
let me grab this and draw a chart. It won't take long,
That's
but
fine.
it'll make a lot of sense when I do this. So the problem is your brain's been changed. Your brain has been trained to look at the graph and make decisions based on the graph. And what you really need to do instead is make a number line and call this the second derivative. And there's one at -2, 0, and 1. And I'm gonna go ahead and put in the signs here. This one's plus because it's above, minus because it's below, minus because it's below, and plus because it's above. Now, if you just looked at this right here, and I told you an inflection point only occurs when it goes from plus to minus or minus to plus, you would tell me there's only an inflection point here and here. But when you look at the graph, you're trained to like look for, like you just said, concave up, concave down, or mins and maxes. It really depends on what you're given. There's like 3 different sets of rules, whether you're given F, F prime, or F double prime. So what I recommend doing is not looking at the graph, making a sign chart.
Yeah, that looks a lot more just better.
Yeah.
It looks better. All right, I'll share screen real quick. Here we go.
These right here. Okay. How do I want to do this? All right. So the boy, how do we want to do this? This is such a weird problem. Okay, so the first graph, I'm sorry, the first graph. Do you see where it says y prime? Well, there's 2 places it's y prime equals 2. There's a dashed line. Do you see that?
That's
See
it.
the dashed line down the middle? Okay, that's the first thing that's kind of similar. So on the right, it says y prime greater than 0. What that means is the function is increasing to the right of that dashed line. So we'll go down to graph 1, and do you see how it is increasing to the right of that line?
And then it has this weird twisty thing.
We'll get to that. Do you see how graph 2 is also increasing? Graph 3 is also increasing. Graph 4, or that last one is not, though. You see that last one is decreasing?
Yeah.
Okay, so scroll back up. Now let's go to where on the left, it says y prime equals 2 to the left of the dashed line. Yeah, so what that means is the derivative has a slope of 2. I'm sorry. The derivative is 2 means the original function has a slope of 2. So go to that first graph and go left of that line. Does that line have a slope of 2? Possibly, right?
So 1, yeah. 2,
Possibly.
1, 2, 1, yeah.
Let's look at the next one.
Work.
What's the slope of a horizontal line?
Nothing.
0. And the next one has a slope of a horizontal line. That's also 0. Okay.
This could work, but this can't work because this decreases.
Right. So we're down to the like first and the fourth. Okay. So now let's go to the lower half where it says y double prime equals 0. So there is an inflection point. No, I'm sorry. There's potential for an inflection point there, but let's go to the one on the right. See where it says y double prime less than 0?
Yeah,
That means it's concave down to the right of that dashed line. Is that graph concave down?
that'd be the only one that would work. Oh
But it
wait,
can't-
no, it wouldn't. No, the other one can work too.
But we're excluding some, right? We're down to one in D.
Mhm.
So it looks
Yeah,
like
so
it's
either
D.
one could work.
Well, no, it's not the set. We're excluding some. Like
Oh yeah.
that's what I was trying to talk you through is you have to
Oh yeah,
cross
never
some
mind.
out.
I wasn't looking, I wasn't thinking clearly. I didn't
Yeah.
realize that this was going concave up.
That's
All right.
concave up, right? So, and we spent a lot of time on that, but if you needed to, you could just click through it. But
You're
your
not gonna
test,
learn if you do
yeah,
that.
yeah, your test question generally is to actually make a graph based
Mhm.
on that like information. They would say sketch something that works. All right. So we should have done this type of problem first. So when you're looking at the original function, which is a, and they want the inflection points, okay? The inflection points are where it changes from concave down to concave up.
All right.
So you have to click on the points.
Which ones would apply here?
So
Would this count?
no, that's a max.
Yeah.
So what I'm go to that second point. See, to me, that second point is where it switches from concave down to concave up.
Oh,
It could be the one below it. I'm not really, those are a little bit harder to tell, but maybe there. And then keep going to the right. So one of those two is a change in concavity. I'm going to say it's the second one, maybe. I really, and then
looks like this is where it starts to
yes,
change.
yes. Okay. So that's for the first derivative. Now, I'm sorry, for the original function. Let's go to C, part C, the third graph. And we just did this. So it's an inflection point where it crosses. Where it
Oh.
crosses the x-axis, where it changes
So
from positive to negative.
would it be
Yeah,
here
yes,
and then here and
does not
that
cross
wouldn't
there.
work. Okay.
Does not cross. Okay. And so remember I said there's different rules for each one.
Yeah.
So when you're looking at the derivative, the inflection points occur at mins and maxes.
Mhm.
So
Oh, would this just be
there's
this,
one,
this, and
yes,
this?
and there's one more.
Oh, there's, oh, never mind.
Right.
There.
Now the rules don't overlap. So like that's why it's confusing. You got to like reset your rules based on, which graph you're given.
Mhm. Yeah, let's take a look at
Yeah.
how
And
what
A,
it thinks.
I don't know if A is right.
Yeah.
We'll see what they,
Yeah, it's this one doesn't work. What? Oh, great. Let me try it again.
yeah, just get back there. And
Yeah, it really doesn't like me. All right, here we
so
go.
I'm guessing it's either one or the other. That one's fine. I think that
Yeah.
one's, and it could be that one. You may have changed them both, and you may get the same answer. You might have only wanted to change one and see if it got better.
Yeah, this is kind of a game of mix and match, I guess. Maybe both?
No, that's not both. But you're going in circles here. You gotta
Yeah.
decide which one it is. Is it that one?
I would say it's right here. Then it would start from right here.
Okay.
Great. Maybe you're right, and it was like one of these instead. There we go. I don't know why they do it like that. It's really weird. Here we go. Length of a human fetus. Where the units of f prime of 39. Right here? Is that what it's talking about? Or like right here?
Sorry, let me get back to your I just did which one? I'm sorry, what are you asking about?
So what is F prime of 39 here?
Well, they
Oh
want the
wait, oh,
units.
never mind, the units.
Units is y over x, whatever y over x is.
So y over x, so length. Um, so centimeters per week. Is that per week? Yeah. Centimeters per week. What's the biological meaning of F prime of 35, 39? Would that be like right here? F prime of 39, or would it be right here?
It's neither. It's the slope. It's the slope of the curve at 39. Yeah,
Oh,
but they're telling you what it is. They're telling you it's 0.5. They say f prime of 39 is equals 0.5. That's given in the
okay.
problem. So the interpretation, this is like what you're going to have to do on a test. You have to write a sentence. So 39 is the week.
Week 39.
Yeah, at week 39. So it's either A or B. And then it's always a rate. So that's why A is correct, because A says rate, not B, not B. No. B, A says a rate.
Because you can select all that are correct.
Oh, I thought I was assuming it was just one. So yeah, it looks like
Maybe.
so that is true because that's the well, at week 39 the fetus no no, because at week 39 it's not 0.5. Between weeks 38 and 39 the fetus will grow approximately 0. So that's true, I think, because that's true because the slope, they're saying like that is the slope there. You can try that if you want.
Oh no, what's going on? Oh,
We didn't get to the
basically,
third. We didn't get to so the last one looks like it's also correct. Let's see why. At week 39, the fetus is growing at a rate of 0.07 centimeters per day. I don't think that is correct because it says it's growing at 0.5. Oh, centimeters per week. Okay, so I think if you take 0.5 and you divide it by the number of hours in a day, 24, you get 0.07. So they just changed the units on you. Nope, that didn't work well. Okay, that didn't
oh,
work.
that's very real.
Oh, and they change anyway. So that's a oddity. Maybe they also changed from inches to centimeters. Okay, so the inflection point is where it goes from concave up to concave down, and you gotta like roughly pick the x value where that occurs.
Looks like 17, maybe 17, 16.
I would say around 16. I mean, I bet that I mean that's probably reasonable to say 16.
It just does it completely black. All right.
Okay, so at the inflection point, it is growing the fastest. It's the change. It changes from where it grows so let me look here. The fetus increases length fastest during the week. Inflection point occurs. Okay, so it's not C because it does not stop growing during that week. So I believe it's where I want to say I guess this could be more than one.
Yeah, this is a more than one
Yeah.
type of question.
Faster during the week in which the inflection point occurs than at any other times. So that's true. So that's A. A is true because it's increasing the fastest at that point in time.
Rate of growth.
Which I would tend to mean that B is not true. C is not true, and then we got to choose between the last two. Its growth is a maximum at the inflection point. Like that's when it's actually growing the fastest. So
All right. Trying to think of if I wanted to do something else. Trying to, or if maybe I kind of want to reserve it for tomorrow.
I'm pretty busy tomorrow. I mean, I don't know that I can give you any kind of courtesy time tomorrow. I've got almost a full schedule, I think, already.
Oh, okay.
But
Let me see
yeah,
if I can.
if there's something else, we can gladly use the next 20 minutes on whatever you would like.
All right, this will be a study guide. This looks pretty difficult. Here we go.
And if you're asking me, we should definitely do some more problems where you have to actually calculate the inflection point. But all right, so could you scroll down to the next question?
Mhm.
Could you scroll down? Just that graph's irrelevant at the moment. Yeah. Okay. Wow. Let me grab this and we can look at this, I suppose. I don't think you're gonna like this, but we'll do it. We'll at least look at this. So, all right, let me share my screen. All right, so this first question, they want you to determine the derivatives for each of these. Okay, so
Oh.
like, and then just fill them in here. So we'll do them one at a time. That first one looks the worst, but it's not that bad. But I'm gonna just for in the having some room here, I'm gonna go down. So this is the first one. Okay, and it's kind of formatted weird, but it another way to write this is it's 10 times, sorry, I got the wrong color. Blue. It's 10 times e to the 2 minus t plus 1 to the minus 1 power.
Okay.
So the derivative of this, the outside function is this minus 1. Okay, so if this is y prime is, you bring this negative 1 down. So it's 10, and then it's times the negative 1, e to the 2 minus t plus 1, and then you subtract 1 from the exponent. Is that okay so far? Because there's more.
Yeah.
Okay, now you got to take the derivative of the inside function. The inside function is an e. What's the derivative of e?
It's just by itself
It's
times
itself.
the
Yep.
negative t.
We're going to get to that. Plus 1, the derivative of that's 0. So the derivative of e is itself, but then you have to multiply by the derivative of the inside function, which is 2 minus t. What's the derivative of 2 minus t?
So it looks like just negative 1.
Just negative 1.
Okay.
So all of this awfulness is your derivative. Now it does get a little better because you can kind of mix and match. So your negatives negative there makes positive. You got 10 e to the 2 minus t over e to the 2 minus t plus 1 squared. So that's your nicely formatted derivative if you want that. Okay, so the next one's somewhat better. I got to snip it in so we can look at it. Okay, so this is your second derivative, or I'm sorry, this is your second piece of the piecewise. And it too would be best served to do a rewrite. It's really t minus 4.676 to the power of
-2.
-2. The derivative is, bring the -2 down, t minus 4.676 to the minus 3 power. The derivative of the inside function is 1.
Oh. Oh yeah. Okay, let's do that. And we would do that for the other 3 down there.
Yeah, I mean, we should keep going because this, unless, but these are, the next one you know how to do. Let's go to the fourth one. Because this one has the appearance of being more difficult than it actually is. A lot of disguise, like, oh, wow, this is really hard. And you do know how to do it. Okay, so the like this out in front is just a constant.
Oh.
So the derivative I mean, you may not like it. Like you're like, oh, why can't it be nice? Well, just isn't. That's your derivative out from.
Okay,
What is the derivative of ln? The if y equals
1 over
natural log,
X.
it's 1 over u times
Oh,
u
1 over
prime.
U.
So
Oh,
it's 1 over t over 90 times the derivative of the inside function. What
which
is
is,
the derivative of that inside function?
isn't that technically just, wait, so if you simplify T over 90, is it just,
Don't worry about that yet. We'll
90
get to
times
that.
T?
What's the
Oh.
derivative in the inside function?
Mhm. Is it just by itself or does it do something else?
Well, so the d dx of a constant times x is
It's
the
the
constant.
constant.
And like one of the things like you're not seeing here is that this is the same as x over c. Well, one, this is, so it really is 1 over c.
Oh, you get rid of the T? Okay.
That's right, because your derivative of it doesn't, because you're looking at it as
Oh,
just t,
yeah.
it's really 190 times t,
Mhm.
and your
And T
derivative is
would
190.
would just leave.
Yes.
Okay, I see what you mean. I see what you mean. Thank you.
Okay, and so you can absolutely simplify this, but you're gonna hear this in class. It'll say, do not simplify.
Mhm.
That's a fairly common thing because these derivatives get so complicated that you spend so much time simplifying it. It doesn't. It
Doesn't really do
takes,
much.
yeah. So for this last one here, what's the derivative of a constant?
Con, is it just 0?
Just 0. So the like this one here, you gotta, if you want, you can fill this in, of course, but they just want you to fill in the derivatives we just did
Okay.
for that.
You want me to screen share for number
Yep.
2?
Yep. If you want us
Alright.
to look at the next question, to be a good idea. I can also make up some questions for second derivatives, or we can keep going through this 3 is a good question. Oh, 3 refers back to that table. That'll be a little messy. Can we go to 4? Is that all
Sure.
right with you?
Yeah, you can cherry pick these because we're
Okay.
low on time.
Where's my snipper? There it is. All right. Ooh, okay. So yeah, there's a lot here. All right, let me share my screen. Okay, so it says find all critical points of f of x, g of x, and so on. I was just going to have us find the derivatives at a point.
Mhm.
So basically like working on your product and your quotient rule. To determine critical points, that's a little harder to do. So that I'd like to stay away from that. But like if yeah, actually, I guess let's do that. Let's do what it actually says here. So let's look at f of x. A critical point is when f prime of x equals 0. So when you go to the derivative row, what x value is the derivative 0?
Go to the X. Okay, so
So do you see how when x is 1,
mhm,
f prime of 1 is 0?
I see that.
So the critical point is when x equals 1. Is that okay?
Yeah, that's good for now.
Okay, now you can actually use that point to go back and find the y value because f of 1 is 2. That's the y value. That means y equals 2. So there's a critical point at 1 comma 2. Is that okay?
Yeah, that's fine.
All right. So we can do the same thing for g of x. G of x. So the critical point is where g prime of x equals 0. Does it ever equal 0?
Is G prime of X ever equals 0? Is that what you
Yes.
said?
You're looking at this. Yes. You're looking at this last row here. Does it ever
Oh,
equal?
I don't see 0 in there.
So this one, there's no critical point.
Okay.
All right. Okay. So the rest of these, let's not get into that. Maybe we'll take away from this. Why don't you share your
Yeah.
screen and see what else we can pick that might be worth looking
That's
at.
like stuff that's actually useful, as in like needlessly hard and complicated.
These are so odd. Could you scroll down, see if there's any others?
Mhm.
These are so odd. Okay, let me just do some second derivative practice with you. You will find this useful.
Way more, yeah, more useful than
All right,
that.
so
Yeah,
let
I
me-
was just thinking to myself, like, I like it more when you mix up like the derivative problems.
yeah. Okay, so let's look at something that you know really well. Y equals sine x. Okay,
Yes.
and we're going from 0 to 2 pi. All right.
Mhm.
What is the derivative of sine?
Derivative of a sine. I'm not sure.
Derivative of sine is you've not done this yet. I see. Okay, I'm sorry. So you derivative of sine is cosine. Where does cosine x equal 0? So this is unit circle. Now, I assume you're gonna get some trig in this class.
I think soon, but haven't had
Okay,
anything like
okay.
this before.
So cosine is 0 when the x value is 0 in the unit circle. So that occurs here at pi over 2 and 3 pi over 2. Do you see that?
Yeah.
Okay, so if we make and this time it's not an infinite number line, you just go from 0 to 2 pi, and you put in this pi over 2 and 3 pi over 2 here, and this is your derivative. We want to figure out where it's increasing or decreasing. So we're going to test points in each of these regions. And I'm doing this specifically because you will get some trig at some point. We might as well like get a handle on it sooner than later. So at pi over 4, what is the cosine of pi over 4? Do you remember that at all?
Cosine of pi over 4. Which part of the number line is it? Is that 60?
That's at 45 degrees. That's right there.
Oh, that one was like, was it? It was something like 3 pi over 2.
It's a root 2 over 2.
Oh, root 2 over
Okay.
2. Okay.
So you may need to brush up, but that's positive. Do you see that?
Yeah, I do.
Now at pi, the cosine of pi is actually negative, and then here the cosine ends up being positive. So is pi over 2, is it a min or a max?
Pi over 2 minimum or max. Looks like, so what was it? So positive to negative. Is that
You
a
might see
minimum?
like it's increasing and then it's
Mhm.
decreasing. Like
Oh,
you,
that's a
you almost want,
maximum.
so
Oh,
it's a
okay.
max, and you almost want to trace it with your finger. Okay, and then here it's a min, it's going down, and then coming back up. That's a min.
Man. Oh, okay.
All right.
I don't know why I'm not doing that in my head. I need to do
Yeah,
that.
there's this, I hate these things, but it's like you can lead a horse to water, but you can't make it drink. Like I want you to do these things, but until you like fully commit and do it, it's just gonna be me telling you and say, hey, please do this. So
Mhm.
um, let me grab one last problem or maybe two here and see if we can come up with some of these. So let's look at some polynomials. These seem to work out more nicely for us. If your trig does come up, you will definitely want to do a refresher on that because it's used enough in this course that you want to look at it. So give me the first derivative here of this function.
Looks like 3x squared minus 6x. Yeah, just 6x.
Okay,
And you leave it.
let's set it equal to 0. Let's find the critical points. Okay, so what can you factor out of both?
3x and then x minus 2.
So
And
what are the two
just one critical
points?
point, and it's just 2.
There's 2. You got to set both of them equal to 0.
You can do f double prime of x.
Oh, not yet, not
Oh
yet.
wait, not
So
yet.
what are the two critical points?
Oh, 0 and 2.
0 and
And
2.
then you do the little number line thing.
Yes. So what are you going to test? Which points do you think are worth testing here?
Looks like -1, 1, 3.
perfect. So I want you to test those in the factored form up here. And I want you to give me the signs at each of these.
Looks like -1 is positive, and then with 1, so 1, -1, that one's negative, and then for 3 minus 2 is positive.
Good.
All right,
Now, is 0 a min or a max or neither?
so positive to a negative is a minimum.
You're
and
going
then-
up, and then you're going down.
Oh, never mind. Oh, okay, then that's maximum.
Okay. How
I did
about
that
a
completely
2?
backwards. All
You're
right, and
going
then
that-
that's a minimum.
That's a minimum. Okay, now if I wanted the y value of the max, so right now there's a max at x equals 0. How do we find the y value? We have to go back to the original function. Do you see that? Like, this just tells you where it is, but you want to know what it is. You put 0 back into the original to get that. And if I want to, if I know there's a min at x equals 2, you got to go back to the original function and plug 2 in to get the max value. Is that okay?
Yeah.
All right, so let's do the same thing for this. Let's find the second derivative. Give me the second derivative, please.
Second derivative would be 6x minus 1, or what would you do there? Oh, just 6.
Yes, set it equal to 0. What is the critical point?
Critical point is this would be like 6 times x minus 1.
Right. So you're solving for
1
x.
0.
Just 1. There's
Okay.
no critical point. You don't set the 6 equal to 0. It doesn't have an x in it.
Oh, I forgot about that.
Okay, so now this does not guarantee that there is an inflection point. You've got to test points on both the left and the right. Okay, so like we might test 0 and 2. What are the signs that go in here? And you're testing them back, in this factored form here.
Where the signs are going in there. Okay. So when you plug in 0, you get a negative, and then when you plug in 2, you get a positive.
So there's an inflection point at x
1.
equals 1 because it changes sign there. Right. So I think that probably does it for today. I would definitely recommend we do more second derivative practice if we have more time in another lesson. That just you're going to do this over and over again in this course.
Yeah, I set up a lesson for tomorrow at
Excellent.
6. Are you gonna be able to do the Whole Foods, or do you want to do online tomorrow?
I'll let you know if we meet in person, it would only be 50 minutes because I got a ton of virtual lessons on the
Yeah,
book.
that's
So
fine.
I'll get back to you. If you'd like to meet in person, I'll try to make it work tomorrow.
Sounds great to me.
All right. Thanks, Jack.
Thank you for your time. Have a
Okay, bye.
nice night. Bye-bye.